right, guys. So this is our third lesson, talking about the rates of change and behavior of graphs. And this is a really good kind of, it'll feel very basic with the calculations we do. And especially at the end, you'll see it's a overview of talking about different characteristics of functions. But the nice thing is that even though this will feel somewhat basic to start, this is good prep for some of the first concepts that you'd see in a calculus class. So hopefully this will feel straightforward enough that when you get to that next year, you'll feel really good about it. So a quick little thing about rates of change. So the rate of change that you've been working with for many, many, many years in math is slope. That's what you notice when you look at this formula here, that delta y over delta x, that's the change in y over the change in x. But it's not always slope. And we'll talk a little bit about why that kind of connection will happen just naturally. But essentially, it's looking at, for rate of change, how an output changes relative to an input. Okay, so you can have any different units as long as you're looking at the change in the output relative to the input value. Okay, so here are some examples. The first one is not my favorite idea: a population of rats increasing by 40 rats per week. That sounds scary enough. And then other examples, that pretty common ones that you'll see a lot, obviously, about a car traveling at 68 miles per hour. That's probably the most basic one in our life. Now, how to actually calculate this. So to calculate this, you need to first off find your values for your outputs and your inputs. And then once you have that, you're going to use that formula up there, which is, again, just the slope formula, to find that rate of change. So let's do an example here about gasoline costs, which is very appropriate right now since gasoline is very expensive. So it's asking us to find the average rate of change between 2005 and 2010. So when they give me those years, they're telling me the first thing I should do is figure out what are the actual ordered pairs for this formula that I'm going to use. Well, I know my x value is going to be my years. All right, I'm going to use the table to find the average cost in dollars of gasoline at those years. So in 2005, it was $2.31 on average. And in 2010, it was $2.84 on average. So just pulling those from the table. So to find our average rate of change between these 2 years, I'm going to do the change in my y over the change in my x values. All right, so again, you can use your phone as a calculator or go to Desmos if you want to do the subtraction here, but you probably could do this numerator in your head. That's going to be 0.53 over 5. And I am going to simplify that. I'm going to finish the division, but just for a moment, let's just pause to think about what this means. This means that over those 5 years, the average change in your price per gallon of gasoline is 53 cents. All right, so we're saying at over 5 years, we would expect gasoline to increase in cost by about 53 cents per gallon. Okay, now it wants the change per year, so I'm going to divide that 0.53 divided by 5 to get 0.106. So we're saying that on average, each year from 2005 to 2010, the cost for gasoline went up by 10.5 cents, or roughly. Now, let's be clear here, right? We could find that actual change from 2005 to 2006, 2006 to 2007. You guys know that the change is not going to be the same each year, but over the course of those 5 years, the average change is about 10.5 cents. So I'll write down a statement here that kind of summarizes that. So from 2005 2010, the cost of gasoline increased on average by 10.5 cents per year. All right, so there's many different ways to describe this, but I just want to show you that this idea can be written as a statement. Okay, let's use a graph. It wants us to find, and this number kind of got cut off there, sorry about that, -1 to 2. All right, so we're going to find the average rate of change on the interval -1 to 2. So they're giving us the x values. So I'm going to go ahead and write down my x values here. But I need to use the graph to find the y values. So -1, 4, and 2, 1. So now if I do my formula, right, in this case, it's the slope formula, so 1 minus 4 over 2 minus -1. That's going to give us -3 over 3, which is an average rate of change of -1. Now, let me show you something real quick to kind of connect it to that idea of slope. So if I were to go look over here and connect these points, right? If I connect those points with a line, you might think, okay, interesting. So we have it connected, right? And if you were to find the slope of that line, you should not be surprised to find that slope of the line is -1, right? Going up 1, left 1 gives me a slope of -1. So that average rate of change is showing you what that slope of a line would be if you were to connect those 2 points. Let's try letter C. So it wants us to find the average speed over the first 6 hours of Anna's trip. So we've got her hours. So before she starts, her distance from her house is 10 miles. All right, so she picked up a friend before leaving. And then after an hour, she's 55 miles from home and so forth. So the first 6 hours would be she's 10 miles from home to start the trip. And then 6 hours later, she's 292 miles from home. So we want to find the average speed, which is going to be the change in our distance, which is our y value, miles, over the change in our x, which is time. So I have 292 minus 10 over 6 minus 0. So that's 282 over 6. Now, I just actually couple days ago, got back from driving from Missouri back home to Texas. And this was not something I was thinking about, obviously, because I'm just driving. But this idea of 282 over 6 is saying that after 6 hours, she is 282 miles from home. So if she drove another 6 hours, we would expect her to be another 282 miles from home. That is a rate of change, but most of the time in our society, we like to think of it as in just 1 hour. So we're going to go ahead and divide so we can get this rate or speed in terms of in 1 hour, which is 47. All right, so 47 miles per hour. Now let's be clear here as I write this down. All right, we're not saying that she's driving 47 miles per hour the entire time, right? She doesn't have cruise control on that. There's probably parts, like I was driving on 59 a lot for this trip, and there are parts of 59 where the speed limit is 75 miles per hour. And there are parts of 59 when you go through small towns where it's 35, 40 miles per hour. So, that fluctuation causes, obviously, your average to change. So at some point on her trip, she's going to be driving faster than 47 miles per hour. And then at some point, she'll be driving slower. So what we would say for our answer here is Anna's average speed over the first 6 hours is 47 miles per hour. All right, let's find an average rate of change when they just give us a function and the interval over which we want to find it. So I'm going to find my points by plugging in 1 to this function. So that's 1 minus 2 times the square root of 1. Square root of 1 is 1. 1 times 2 is 2. 1 minus 2 is -1. So my ordered pair here is 1, -1. Let's plug in 9 as well. So 9 minus 2 times the square root of 9. The square root of 9 is 3. 3 times 2 is 6. 9 minus 6 is 3. So my ordered pair is 9, 3. So now if I use my formula for the change in the y over the change in x, 3 minus -1 over 9 minus 1. So that's going to be 4 over 8, or 1/2. Okay, and you don't have to do this, but I just want to kind of connect it, hopefully in your brain, to what we're talking about. So if I were to graph this function, x minus 2 times the square root of x into decimals, so I'm going to do right now. So we have x minus 2 times the square root of x. Okay, and I'm going to duplicate it to make a little table here. So I've got 1, and then I'll just use some other ones. 1, 4, 9. Delete these. Okay. All right, so if I look at it, my point was 1, negative 1, which we found, and then 9, comma 3, which we already found as well. All right, and if you were to make a line through there, all right, you would find that that slope, all right, would be positive 1/2. Okay, so I don't want to get too complicated here. All right, let's see. Move it down. Almost. It's going to be, looks like it's a decimal in there. All right. Well, I found it. Good. Minus 1/2. So you can see that that slope of 0.5, that 1/2, is that slope between those two lines. Okay. All right. Let's keep going. All right. Now, the last part that we're going to be talking about is increasing, decreasing, where functions are constant as well. And then from there, looking at different extrema, which is just a fancy way to say what are the local maximum and minimum values that you find. Okay, so if we look at a function and we see that over a certain interval, the y values of a function are getting larger as we move to the right, then we say the function is increasing. If we look at a function and we see that the y values are going down or getting smaller as we move to the right, then we say the function is decreasing. Okay. Now, based on this, you can have what are called local minimums and local maximums. So they're not necessarily the highest or lowest value of your function. Like this graph here shows you that we're going to positive infinity and negative infinity in the y values. But if you were to just look at where you're going from increasing to changing to decreasing, we would call this a local maximum. And then as we move from decreasing to increasing right here, this is called a local minimum. And again, it's one of those things where this is kind of the, learning like the alphabet. So when you get to calculus, you can do even more stuff with this information. All right, so in terms of, writing down that local maxima and local minima, right, what I would say in my brain and what I know is that a local maxima occurs when the function changes from increasing to decreasing. All right, the local minima, obviously very similar. Your function is going to be changing the other way. So that occurs when the function changes from decreasing to increasing. And local extrema is just the fancy way, as I said, of finding those local maxima and local minima. And when you say maxima or minima, that's the plural. If you say minimum or maximum, that would mean one of them. So this is just your local maxima or local minima. All right, so let's give this a try. So we look at this graph here and it says, identify the intervals on which the function appears to be increasing and decreasing. So when I look at this, it's up to you. I get different students, different teachers will tell you they'll just start from the left and the right, and whatever happens first, they'll start with. Like in this case, this function is actually decreasing from the beginning. I just in habit have always just written INC and DEC, but it doesn't matter. I don't really care. So in terms of where this function is increasing, I'm looking for the y values getting higher or greater as I move from left to right. So I notice that I'll kind of use a different color here to help, that we're increasing from 1 to 3. So from 1 to 3, again, it's all about the x values here on these intervals. And you'll notice I don't care about brackets or parentheses. So just always use parentheses when you're writing intervals for increasing or decreasing about your function. And then it's increasing from 4, going all the way to the right to infinity. Now, in terms of decreasing, so decreasing, again, as I said, we're actually decreasing from the very beginning all the way until 1. So negative infinity to 1. Again, focus on writing the x values. I know that that piece of the function is actually going up towards positive infinity, but you're starting the farthest left, which means you're starting at negative infinity. And then we're decreasing from 3 until 4. Now, this problem doesn't ask us to find the local extrema, but again, your local extrema is going to happen when you're changing from your increasing to decreasing or decreasing to increasing. So right here we're changing, right here we're changing, and right here we're changing. So we'd actually have 3 points that would fall under the local extrema. Okay, the next one. It wants us to graph this function to find the local extrema and then determine the intervals on which the function is increasing and decreasing. So let's go ahead and go to Desmos. I think that's the easiest to use. Yes, you have a TI-84 in the classroom, or even you could download the app on your phone that gives you a free TI-84. But in this class, I'm going to be pushing Desmos as much as possible. So let's delete this and type in x cubed minus 6x squared minus 15x plus 20. Okay, and I can't really see that. So what I always like to do is I duplicate it and make a table, and then I hit this little magnifying glass, and that makes it look a little easier. Still can't see much of it, but if I zoom out just a little bit, then I can kind of see what's going on. Okay, the really nice thing about Desmos is that you can literally just, you see that it's increasing to start, and it looks like it's changing up here as in terms of our from increasing to decreasing. So there's a local maximum. And then same thing here, it'll actually give you those points for your local extrema. So I've just plotted my negative 1 comma 28 is the local maximum, and 5 comma negative 80 is the local minimum. All right, so I'm going to write those down, and then we'll get into the intervals for increasing and decreasing. So I said the local, let's see, where'd you go? There you are. So the local maximum said was negative 128, I believe. Confirm. Yes. And the local minimum is 5 comma negative 80. All right. And then in terms of my intervals where the function is increasing and decreasing, as I said, we're increasing from the very beginning. All right. So I'm going to be going from negative infinity into that negative 1. And then in terms of my other part that I'm increasing from 5 to infinity. So I'm increasing for pretty much the entire part of the function, except for that middle piece between negative 1 to positive 5, and it's all about the x values, where the function is decreasing. All right, so that's really kind of the process I want you to focus on. Let's do one more example, kind of putting it all together from every piece of this lesson we've been discussing. So finding the average rate of change using this graph. All right, so I need to find ordered pairs here. So when I go to 1 comma 5, and then for 4, that's 4 comma 4. Using my formula, the change in y over the change in x, I get 4 minus 5 over 4 minus 1, which is negative 1 over 3. So my average rate of change between those 2 points is going to be negative 1/3. So if you were to plot that, that kind of makes sense for this line that connects them, right? The slope is negative and it's pretty shallow, so it's very small, negative 1/3. Okay, increasing intervals. This can be a lot here. So I'm going to use that color coordination again. It's up to you if you want to do this or just read it. So we're increasing from the very beginning. And notice there was an arrow there, so I'm going to be starting at negative infinity. So increasing from negative infinity to 1. All right, then I'm decreasing for a little bit, then increasing again from 3 until 5. And then finally from 7 all the way forever to infinity. And again, just to remind you, when I write that infinity, I'm talking about to the right forever. Okay, so then when I'm ready to look at the decreasing intervals from 1 until 3, and from 5 until 7. All right, so the only two intervals for decreasing. Now for the local extrema, this is where, again, I'm looking at where do these values or intervals change from increasing to decreasing and vice versa. So that would occur here. There's a local maxima. Here's a local, a local maximum, a local minimum, a local maximum, and a local minimum. So I've got 4 extrema. So let's just do the local maximums first. That's going to be 1, 5 and 5, 7. And the local minimums is going to be 3, 1 and 7, 3. All right. Now, for this last part, take 30 seconds just to talk about absolute maximum and absolute minimum. Because I know I kind of colored over it, but because these had arrows going in both directions, that means we're going to approach in our y values negative infinity and positive infinity. And whenever you have a function that in your y values goes up and down forever, you actually do not have any absolute maximum or absolute minimums. Okay, so in this case, we do have local extrema, but we don't have any absolute extrema. So when it says if possible, they're just thinking, is the function going up and down forever? So I'm actually going to write that there are no absolute maximum or minimum. All right, and that is it. All right, good luck on the practice.